Hi guys, today I want to talk about nuclear decay. Now, nuclear decay is a natural process. The driving force behind it is that atoms want to be stable, and when they have the improper ratio of neutrons to protons in the nucleus, they're not stable, and so they decay in order to become a stable atom. There are multiple ways that they can do this, but two of the most common are alpha decay and beta decay. Now, alpha decay involves a parent atom that emits an alpha particle, and this is the alpha particle. It's a helium-4 nucleus. It includes two neutrons, which are the green, and two protons, which are the red. And when we emit this alpha particle, or this helium-4 nucleus, we create a daughter atom. And the daughter is going to be a different element than the parent that it came from. The second way that we can decay is known as beta decay. And beta decay involves one of the neutrons turning into a proton while emitting a beta particle. This is a beta particle. A beta particle is also just an electron. And that's why you see the mass is 0. And an electron has a charge of -1. So the -1 takes the place of what would normally be the atomic number of an element. And then the lowercase e stands for electron. But again, even with beta decay, the daughter atom is an entirely different element than the parent from which it came. Now, something that never changes is mass. According to the law of conservation of mass, mass is always conserved, even during these nuclear reactions. So whatever total mass we start with is going to be equal to the total mass that we end with. And we can use this knowledge to help us solve for missing pieces of nuclear reactions. But before we get into that, let's double check that that's actually true. So in my alpha decay example here, radium-222 was my parent, and polonium-218 was my daughter, along with the alpha particle. Now, if conservation of mass is true, that means that what I started with on the left side should equal what I end with on the right side. So my arrow becomes my equal sign, and I think of the top row of mass numbers as one math equation, and the bottom row of atomic numbers as a second math equation. So 222 is equal to 218 plus 4, and that is true. Along the bottom, 86 is equal to 84 plus 2. And that is also true. So here, from the beginning to the end, mass is still conserved. We didn't lose anything. Let's check our beta decay problem. Again, from the left side to the right side, I should have the same amount of mass. So 8 is equal to 8 plus 0. Well, that's true. And 3 is equal to 4 minus 1. Well, that's true too. So beta decay also shows the conservation of mass. Let's look at some more problems. So as I mentioned, we want to think of the arrow as the equal sign, and we always want the left side to be equal to the right side. So in this first problem, carbon-14 is my parent, and I'm spitting out an alpha particle, or the helium-4 nucleus. And I want to know, what is the daughter atom going to be? Well, first I need to solve for the missing mass number on the top and the missing atomic number from the bottom. So if I rewrite the top row into a math equation, it would read 14 is equal to 4 plus the unknown mass, which I'm using A as my variable for my unknown mass. To solve for A, I simply need to subtract 4 from both sides of the equation. So 14 minus 4 is going to be what A is equal to, which is, of course, 10. So my missing mass number is 10. I'm going to do the same thing with my bottom row to solve for my missing atomic number. So 6 is equal to 2 plus I'm using the variable z to stand for the missing atomic number. So to solve, I'm going to subtract 2 from both sides, and that tells me that my missing atomic number is equal to 4. So now that I know the mass number is 10 and the atomic number is 4 for my daughter atom, I can go to the periodic table and I can look up what is element number 4, and I'll find that it's beryllium. So I put the symbol for beryllium in the middle. Let's look at a few more examples. So here, nitrogen 14 is my parent, and we spit out a beta particle, and I want to know what is the daughter atom going to be. So if I think of my top row of mass numbers as my first equation, I have 14 is equal to 0 plus my missing mass number. I'll keep using A for my variable for my mass number. To solve for A, I'm going to subtract 0 from both sides of the equation. So I'm going to have 14 minus 0 is going to be equal to the missing mass number. So that means that 14 is my missing mass number. To solve on the bottom, I'm going to do the same thing. I'm going to rewrite. And we have 7 is going to be equal to -1 plus my missing atomic number. And I'll keep using z for the variable representing the missing atomic number. So now to solve for z, I need to add 1 to both sides because this is negative. So to get rid of it, I need to add 1. So I'm going to do that. 7 plus 1 is going to be my missing atomic number. So when I simplify that, I find that 8 is my missing atomic number. So 8 is my atomic number of my daughter atom. So then to find my symbol, I just need to go to my periodic table and find element number 8, and I find out that it is oxygen with the symbol capital O. So that is my last step in completing this problem. So my daughter is oxygen 14. Let's do one more, but this time let's solve for the parent. What did we start with? Now, even though we're solving for what we started with, we still use that same logic of whatever is on the left has to equal what's on the right. So in this one, my missing mass number is going to equal 9 plus 4. So 9 plus 4 is 13. So my missing mass number is 13. My missing atomic number, I can think of this as being equal to 5 plus 2. So if I add 5 and 2 together, I find my missing atomic number is 7. So now I go to my periodic table and I look for who is element number 7, And I find that number 7 is nitrogen with the symbol capital N, and that is the last step. So my parent atom here was nitrogen 13. So with decay problems, just remember, whatever's on the left must equal whatever's on the right. So the two sides will always be equal to each other. And you can break it up for the top row of mass numbers, solve for the missing piece on the top, and the bottom row of atomic numbers, solve for the missing piece on the bottom. And then for the symbol, go to whatever atomic number you found on the periodic table, and that is where you will find the symbol. Hope that helped. See you next time.